Hello everyone, I'm Wang, a PhD student at the University of Warwick. Today I will present our paper, PPQ-Trajectory, Spatial-temporal quantization for querying in large trajectory repositories. Large location sequences are being generated by mobile devices and services. The raw trajectory data collected from these devices is a sequence of time-stamped positions, including latitude, longitude, and the timestamp. For the effective management of spatial-temporal trajectories, we need to achieve several objectives, including query-friendly compression on large-scale dynamic trajectories, answering queries without reconstructing the full trajectories, getting higher accuracy for approximate queries, and supporting incremental updates on compression data. We aim to achieve all of these. Our approach is an online quantization-based summarization that utilizes the spatial-temporal properties of trajectory data. Quantization is the process of mapping input values from a large continuous site to a finite site. Usually, we call this finite site as codebook and each element as code word. It's a powerful method for compressing data with a query-friendly format without heavy decompression. We can use this codebook as a summary representation for the input data and take it as our trajectory database. Scalar quantization is a basic type of quantization method for multiple dimension data. It quantizes each dimension separately. For a two-dimension example, we can observe every dimension is quantized into 2-bit. And where DB benchmark paper has showed the scalar quantization-based method with plus file performs the best among alternative approaches for approximate query on large and high-dimensional data. Vector quantization is another type of quantization method. It maps vectors in the dimensional space into a codebook. The left figure is an example of a simple vector quantization. It divides the vectors into groups. Each vector in a group is represented by the group's centroid. This is used to generate a binary code for the vectors. The query is run on the codebook, and the reconstructed result can be generated from the summary. The current quantized based indexing methods, including V plus file, VQ index, etc., are designed for static multiple dimensional data. Here, we aim to develop a spatial-temporal quantization method for dynamic data. We extend one-dimension predictive quantization for spatial-temporal data. We use the prediction function to write new coming trajectory points with respect to the previous one. And instead of quantizing the raw data, we quantize the errors of the predictions. The prediction parameters are chosen to minimize the prediction errors. This can reduce the range of the values to quantize and generate a smaller sized codebook. The prediction parameters and the codebook can be used to reconstruct the raw values as needed. Overall, our solution includes 3 parts. The first part is a partitioned quantizer that generates a codebook with error guarantees and optimal prediction parameters. The second part is a local encoder that maps the error states into binary codes. The third part is a spatial temporal index over the summary, which avoids traversing the full trajectories. Our codebook bounds the quantization error. The code words have never a distance above a threshold to the original point. The figure on the right shows how the subspaces are indexed by the error-bounded codebooks. For predictions, one can use any function. In signal processing, a single prediction function is used for each signal. If the database has correlated recalls, one can use a single prediction function. A better approach is to design different predictions for different groups of trajectories This helps to maintain a smaller number of prediction functions and still have accurate predictions if each partition has similar trajectories. The example here on the left with one prediction function for the whole dataset, we get a codebook of size 4. On the right, the figure uses partitioning and a prediction function for each partition. It achieves more accurate prediction and the size of the codebook is reduced. For grouping the trajectories, one can apply a traditional partitioning based on spatial proximities. Instead, we design an autocorrelation-based partitioning. We put trajectories with similar autocorrelations to the same partition, so they can use the same prediction function. Because the prediction function is also designed based on the autocorrelations, a single function can work effectively for all the trajectories in the same partition. The example on the right here shows an autocorrelation-based partitioning. Each point here represents a trajectory. X-axis is the trajectory point at time t-1, y-axis is at time t. Traditional partitioning on the left puts those records into different partitioning. Here we can observe the dynamic range of the prediction error of the autocorrelation-based partitioning is half smaller than that of the spatial partitioning, so a smaller size codebook is produced. The error space between the original trajectory point and its reconstructed one is represented like this left circle because we have an error bound guarantee. We want to use this bound on the relative positions to further reduce the loss of the summarization. To exploit this, we generate a fine-grained grid with subspaces represented as a tree structure and encoded as a short binary code. With this local encoding, we can reconstruct the relative positions between the original point and its reconstructed one. The error here is reduced to at most half of the diagonal length of the grid cell, and we can get more accurate summarization. So far, we built the quantization-based summary. At the last stage, we built a temporal partition-based index, and the paper has the details how we incrementally maintain this index. Here are some example queries that we execute on our quantized summary. One is spatial-temporal range query, which is to retrieve the trajectories that travel around a certain location at a given time. Another query is trajectory path query to retrieve their following sub-trajectories after a given time. Here is a flowchart to show how the two queries are answered without reconstructing the full trajectories, only based on the summarization and our spatial-temporal index. For spatial-temporal range query, our solution has the smallest mean absolute error, and it can achieve up to 55 more accuracy than the alternative approaches, specifically with local coding and a local search strategy. PPQ-A and PPQ-Is can get precision 1 by checking a smaller candidate list. We also evaluate the performance of trajectory path query against different length prediction. The mean absolute errors of our solution are orders of magnitude smaller than the alternative approaches. In terms of compression, the codebook size of our solution is up to 27 times smaller than trajectory. Its compression ratio is also 2 times that of REST. More results can be found in our paper. In conclusion, our solution maintains an error-bounded summary for large-scale trajectory data analytics. It can achieve significant improvements on the approximate query, exact query, summary efficiency, and the compression ratio. In the future, we can utilize machine learning to predict trajectory points more accurately and generate a more compact summary. Any comments and problems are welcome. Thanks.